Tonight, we're going to explore what would happen if humanity left Earth in 2026 and tried to reach the nearest known black hole. There is a black hole called Gaia BH1, sitting in the direction of the constellation Ophiuchus. It is about 1,560 light-years from Earth. That means even light, moving at about 186,000 miles per second, would need 1,560 years to reach it. Given those numbers, the nearest black hole should feel close only in a cosmic sense. It should be the kind of object that sounds nearby on a map of the Milky Way, but still belongs far beyond any real human journey. Yet instead, when we compare that distance to the speeds of actual spacecraft, something unsettling happens. The closest known black hole becomes almost impossible to reach, not because it is at the far edge of the galaxy, not because it is hidden behind the center of the Milky Way, but because even the nearest one sits so far away that our fastest machines would need millions of years to get there. And by the end of tonight, you're going to understand why reaching a black hole might be less like taking a journey through space and more like trying to build a civilization that can survive long enough to arrive. Gaia BH1 is strange because it does not announce itself the way many people imagine a black hole should. There is no giant glowing tunnel in space. There is no visible surface. There is no dark circle hanging close to Earth where a telescope can simply zoom in and take a clear picture. Instead, Gaia BH1 was discovered because of a star. A fairly ordinary star, similar in some ways to our own sun, was moving as if something heavy and invisible was pulling on it. The star was not sitting still. It was orbiting a hidden companion once every 185.6 days. When astronomers studied that motion, the unseen object appeared to be around 10 times the mass of the Sun. That is far too massive to be a planet. And because it gives off almost no visible light of its own, it fits the profile of a quiet stellar black hole. A stellar black hole is the collapsed core left behind after a very massive star dies. When the fuel inside that star runs out, the outward push from fusion fades. The core collapses under gravity. If enough mass remains, gravity wins completely, and the core becomes a black hole. The result is an object with so much mass packed into such a small region that there is a boundary around it called the event horizon. Past that boundary, escape would require moving faster than light, and nothing can do that. But the most disturbing part of this video is not the event horizon, at least not yet. The first disturbing part is the distance, because Gaia BH1 is the nearest known black hole, and it is still 1,560 light-years away. To put that in perspective, if light left Earth toward Gaia BH1 in the year 2026, it would arrive around the year 3586. That is longer than the time between the fall of the Western Roman Empire and today. It is longer than the entire history of telescopes, rockets, satellites, space stations, and every spacecraft humanity has ever launched. And that is only for light. A human spacecraft would be far slower. The International Space Station moves around Earth at about 17,500 miles per hour. Apollo 10, during its return from the Moon, reached about 24,791 miles per hour, one of the fastest speeds ever reached by humans. Voyager 1 is drifting through interstellar space at tens of thousands of miles per hour. Parker's solar probe has reached about 430,000 miles per hour while falling close to the Sun. Those speeds sound enormous. They are enormous beside Earth. At those speeds, continents shrink, planets can be crossed, and the Moon becomes reachable in days. But against 1,560 light-years, they barely move the needle. A black hole can be the closest one we know about, and still sit beyond the scale of ordinary human time. That is the contradiction at the heart of this journey. The nearest black hole is close enough for astronomers to detect its gravity tugging on a star. But it is far enough away that a mission launched in 2026 would force us to confront a brutal truth. Space is not only vast. It is vast in a way that turns speed, lifetimes, and even civilizations into small things. So before we imagine what the black hole would look like up close, before we talk about gravity, warped light, or the point of no return, we need to ask a more basic question. If humans have actually traveled only at solar system speeds, how long would it really take us to cross a distance built for light? A light year sounds gentle at first. It sounds almost small because the words are so familiar. Light, year. Two simple words we hear all the time. But a light year is a distance. It is the distance light travels in one full year, while moving at about 186,000 miles every second. That speed is almost impossible to picture directly. In 1 second, light could travel around Earth more than 7 times. In 1 second, it could go from New York to Los Angeles more than 60 times. In 1 minute, it travels about 11 million miles. In 1 day, it travels about 16 billion miles. And after 1 full year of moving at that speed, light has crossed about 5.88 trillion miles. That is 1 light year. Gaia BH1 is about 1,560 light years away. So when we say the nearest known black hole is close, we are using the word close in the cold language of the galaxy. It is close compared with the far side of the Milky Way. It is close compared with the galactic center, which sits about 26,000 light years from Earth. It is close compared with the entire Milky Way, which stretches roughly 100,000 light years across. But for a human being, for a machine, for a spacecraft leaving Earth in 2026, Gaia BH1 is still almost 9 quadrillion miles away. That number is so large that it stops behaving like a normal number. The Moon is about 238,000 miles from Earth. That was far enough to define one of the greatest journeys in human history. In July of 1969, Apollo 11 crossed that distance in about 3 days. The astronauts had to leave Earth on top of a Saturn V rocket, a machine taller than the Statue of Liberty, burning millions of pounds of fuel just to send 3 people toward the Moon. And the Moon is still in Earth's backyard. Mars, at a close approach, can come within about 34 million miles of Earth. That is already a mission measured in months. Space agencies have to plan launch windows around the motion of the planets, because Earth and Mars are both moving around the Sun. Miss the right window, and the trip becomes longer, harder, and more expensive. Jupiter is farther still. It orbits about 484 million miles from the Sun. Saturn is about 886 million miles from the Sun. Neptune is about 2.8 billion miles from the Sun. Those distances already feel enormous, but they are still solar system distances. Gaia BH1 lives on a completely different scale. NASA's New Horizons spacecraft launched in January of 2006 and reached Pluto in July of 2015. That journey took more than 9 years. It crossed billions of miles. It gave humanity its first close look at Pluto's mountains of water ice, its nitrogen plains, and its thin blue haze. And yet, compared with Gaia BH1, that entire journey barely moves the needle. To reach the nearest known black hole, you would have to repeat a Pluto-scale journey millions of times over. You would have to cross the familiar solar system, then the outer solar system, then the distant shell of icy bodies far beyond Pluto. And after all of that, the real trip would still have barely begun. This is where the distance starts to become uncomfortable, because light itself needs 1,560 years to make the trip. Imagine a beam of light leaving the Gaia BH1 system and heading toward Earth. If that light reached us in 2026, it began traveling around the year 466. At that time, the Western Roman Empire was near its final collapse. The Viking Age had not begun. The first universities did not exist. The printing press was still about 1,000 years away. Telescopes did not exist. Electricity had not been harnessed. Rockets were beyond imagination. No one on Earth knew that black holes were possible. That beam of light would keep moving through space while empires formed and disappeared. It would keep moving while languages changed, while cities grew from small settlements into capitals, while ships crossed oceans, while maps were redrawn, while science slowly learned that Earth was a planet orbiting a star. It would keep moving through the birth of modern astronomy. It would still be traveling when Galileo pointed a telescope at Jupiter in 1610 and saw 4 tiny moons moving around it. It would still be traveling when Isaac Newton published his laws of motion and gravity in 1687. It would still be traveling when Albert Einstein published general relativity in 1915, giving science the first real mathematical path toward understanding black holes. And only after all of that time would the light finally reach Earth. That is the strange thing about this distance. Looking at Gaia BH1 means looking into the past. We are not seeing the system as it is right now. We are seeing light that left it more than 15 centuries ago. Whatever is happening there in 2026 will not be visible from Earth until the year 3586. So even before a spacecraft leaves Earth, time is already part of the problem. A black hole, 1,560 light-years away, is not just far across space. It is far across history. It is separated from us by a distance so large that the light arriving now began its journey before most of the modern world existed. And that is only the light. A spacecraft has mass. It has structure. It has engines. It has fuel. If people are aboard, it has air, water, food, shielding, heat control, waste recycling, medicine, spare parts, and living space. It cannot move like light. It cannot simply cross the galaxy at nature's speed limit. So the first answer is already brutal. At the speed of light, Gaia BH1 is 1,560 years away. At any speed, humans have actually reached the number becomes something much larger. The distance alone tells us that this journey cannot be understood through miles in the ordinary sense. It has to be understood through speed, time, and survival. So now we need to leave the scale of light behind and ask what happens when the traveler is no longer a beam of radiation, but a human being inside a spacecraft. The fastest humans have ever traveled were not riding in some future starship. They were inside a small Apollo command module in May of 1969, falling back toward Earth after a mission around the Moon. That mission was Apollo 10. It was the final full rehearsal before Apollo 11 landed on the lunar surface 2 months later. The crew was Thomas Stafford, John Young, and Eugene Cernan. Their command module was named Charlie Brown, and their lunar module was named Snoopy. They went almost all the way through the moon landing sequence, flying the lunar module down to within about 9 miles of the moon's surface, then returning to orbit and coming home. On the way back to Earth, Apollo 10 reached about 24,791 miles per hour during re-entry. That is still the fastest speed ever reached by humans. At that speed, you could cross the continental United States in around 6 minutes. You could travel from Earth to the Moon in less than 10 hours if you could hold that speed in a straight line. You could circle Earth in about 1 hour. For a human body inside a spacecraft, protected by a heat shield, guided through the upper atmosphere, it was an astonishing speed. But that number came during a very specific moment. Apollo 10 was returning from the Moon and falling into Earth's gravity well. A gravity well is the invisible slope created by a massive object's gravity. When something falls toward Earth from deep space, it gains speed, the same way a ball gains speed rolling downhill. The command module used that speed to enter the atmosphere. Then the atmosphere itself slowed it down through violent friction, heating the heat shield to thousands of degrees. That was a burst of speed at the end of a lunar mission. It was not a comfortable cruising speed across the galaxy. The crew did not live at that speed for years. They reached it during the final plunge home, while the spacecraft was wrapped in plasma. Radio contact was interrupted, and the heat shield was being burned away layer by layer to protect the people inside. Still, it gives us the cleanest human benchmark we have, so let's use it. Gaia BH1 is about 1,560 light-years away. At Apollo 10's record speed, a spacecraft would need roughly 42 million years to get there. 42 million years. That number is almost hard to accept because Apollo 10 already feels fast beyond human scale. The crew was moving faster than a rifle bullet, faster than any jet aircraft, faster than anything any human had ever experienced. And at that speed, the nearest known black hole would still be 42 million years away. To feel what that means, compare it to our own species. Homo sapiens, meaning modern humans, appeared roughly 300,000 years ago. Some of the oldest known fossils linked to early Homo sapiens were found at Jebel Irhoud in Morocco, dating to around that age. That means our species has existed for only a tiny fraction of the time an Apollo speed journey to Gaia BH1 would require. The trip would last about 140 times longer than Homo sapiens have existed. 42 million years ago, Earth was in the Eocene epoch. Antarctica still had forests in parts of its landscape. Early whales were still evolving from land-dwelling ancestors into fully ocean-going animals. The continents looked familiar, but not quite like today. India had already collided with Asia, helping raise the Himalayas. Grasslands were beginning to spread, but the world of humans, cities, farms, writing, tools, and rockets was unimaginably far in the future. A spacecraft leaving Earth at Apollo 10 speeds would have to travel across a span of time like that before reaching the nearest known black hole, and no human crew could experience that as a mission. The original astronauts would be gone almost immediately on that scale. Their children would be gone. Their civilizations would be gone. Mountain ranges would rise and erode. Ocean coastlines would shift. Species would appear, adapt, and vanish. The spacecraft would still be moving through the dark, covering distance at the fastest speed humans have ever reached, and still needing millions upon millions of years. So the fastest human speed gives us a strange kind of answer. It tells us that human beings have reached astonishing velocities, but those velocities belong to the Moon, Earth, and the inner solar system. They are not enough for the space between stars. To understand travel that humans can actually live through, we need a different comparison. Not the fastest moment humans ever survived, but the speed of the place where humans have lived in space continuously for years. Apollo 10 gives us the fastest moment humans have ever survived. But there is another kind of human speed. The speed of a place where people can actually live. For that, we need to look closer to Earth. About 250 miles above the planet, the International Space Station circles in low Earth orbit. It has been continuously occupied since November of 2000. That means for more than 25 years, humans have been living above Earth every single day. Astronauts sleep there, they work there, they exercise there. They grow small experiments with plants. They repair equipment. They watch thunderstorms, deserts, oceans, wildfires, and city lights pass beneath them. And the whole station is moving at about 17,500 miles per hour. That sounds impossibly fast. At that speed, the station circles Earth about once every 90 minutes. The crew sees around 16 sunrises and 16 sunsets every day. A normal day on Earth becomes a repeated cycle of daylight and darkness, rushing past the windows again and again. From the cupola, the station's windowed observation module, Earth fills the view. The planet does not look like a distant point. It looks huge, curved, bright, and close. Blue oceans, white cloud systems, the thin glow of the atmosphere wrapped around the edge of the world. This is the fastest home humans have ever built, and it gives us a better living benchmark than Apollo 10. Because Apollo 10 was a short burst of speed during re-entry. The International Space Station is a place where human bodies have adapted to living in orbit for months at a time. A typical mission lasts about 6 months. Some have lasted much longer. In 2015 and 2016, astronaut Scott Kelly spent 340 continuous days aboard the station. Russian cosmonaut Valery Polyakov spent 437 days in space aboard the Mir space station in the 1990s. These missions taught us what space does to the human body. Without gravity pulling downward, bones lose minerals, muscles weaken, fluid shifts toward the head. The heart works differently. Astronauts can return to Earth with weaker legs, balance problems, back discomfort, and changes in vision. To fight this, station crews exercise for roughly 2 hours per day. They use a treadmill with straps holding them down. They use a stationary bike. They use a resistance machine that mimics weightlifting without actual weights. The station also needs constant support from Earth. Cargo vehicles bring food, science equipment, replacement parts, clothing, and supplies. Water is recycled. Air is managed. Carbon dioxide has to be removed. Filters have to be changed. Toilets break. Cooling systems fail. Solar arrays degrade. Computers need maintenance. Even in low Earth orbit, only a few hundred miles from home, living in space is a careful, ongoing act of survival. Now imagine taking that same speed and pointing it toward Gaia BH1. At 17,500 miles per hour, the journey to the nearest known black hole would take roughly 60 million years. 60 million years is longer than the time since the dinosaurs disappeared. The asteroid that helped end the age of non-avian dinosaurs struck Earth about 66 million years ago, near what is now the Yucatan Peninsula in Mexico. After that impact, forests burned, sunlight was blocked, food chains collapsed, and mammals slowly began to spread into the empty spaces left behind. Primates evolved. Apes appeared. The human lineage split from chimpanzee ancestors around 6 to 7 million years ago. Modern humans arrived only around 300,000 years ago. At International Space Station speed, a spacecraft leaving for Gaia BH1 would need a span of time almost as large as the entire age of mammals after the dinosaurs. That is the strange failure of orbital speed. It is fast enough to circle the world in 90 minutes. Fast enough to turn sunrise into something astronauts see again and again in a single day. Fast enough to make Earth feel like a moving world beneath your feet. And still, against the distance to the nearest known black hole, it becomes almost motionless. The International Space Station proves that humans can live in space, but it also shows how protected that life still is. The station remains close to Earth, close enough for resupply, close enough for emergency return, close enough for mission control to speak with the crew in real time. A journey to Gaia BH1 gives up all of that. So if human living speed collapses this badly, the next comparison has to leave people behind. The machines we have sent farthest into the dark can travel without food, water, sleep, or fear. And even they struggle against the scale between stars. The machines we have sent farthest from Earth do not need air. They do not need water. They do not need sleep, food, warmth, or a place to stand. That is why Voyager feels like the next natural comparison. Voyager 1 launched from Cape Canaveral on September 5th, 1977. Voyager 2 actually launched first on August 20th, 1977, but Voyager 1 took the faster route. Both spacecraft were built for a rare planetary alignment that happens only about once every 176 years. That alignment let them use the gravity of the giant planets like a series of invisible slingshots. Voyager 1 flew past Jupiter in March of 1979. Then it flew past Saturn in November of 1980. After that, Saturn's gravity bent its path upward, away from the flat plane where most of the planets orbit. The spacecraft was sent toward the dark space between stars. Voyager 1 is small. It weighs about 1,820 pounds. Its main antenna is about 12 feet wide. Its computers have far less memory than a modern phone. Its power comes from plutonium-238, a radioactive material that releases heat as it decays. That heat is turned into electricity. At launch, Voyager 1 had about 470 watts of electrical power. That is less than a few bright household lights. And yet, this little machine has kept traveling for nearly half a century. In August of 2012, Voyager 1 crossed the heliopause. The heliopause is the boundary where the solar wind gives way to interstellar space. The solar wind is a stream of charged particles flowing outward from the sun. For billions of miles, that wind creates a bubble around the solar system. Voyager 1 became the first human-made object to cross that boundary. It entered interstellar space. That sounds like it has left the solar system behind. The deeper truth is more humbling. The sun's gravity reaches far beyond the heliopause, far beyond Neptune, far beyond Pluto, far beyond the Kuiper Belt, where many icy bodies orbit in the outer dark. Out there may be the Oort cloud, a huge distant shell of icy objects surrounding the sun. Some estimates place its outer edge as far as 1 or 2 light years away. Voyager has crossed the sun's magnetic boundary, but it has barely begun crossing the full gravitational outskirts of the solar system. After nearly 50 years, Voyager 1 is still only about 1 light day from Earth. A light day is the distance light travels in 1 day. Gaia BH1 is 1,560 light years away. That is the difference between our proudest deep space machine and the true scale of the galaxy. Voyager 1 is moving at roughly 38,000 miles per hour. At that speed, it could cross the distance from New York to Los Angeles in less than 5 minutes. It could circle Earth in less than an hour. It is faster than any bullet, any aircraft, and any human body could experience unprotected. But if Voyager 1 were aimed toward Gaia BH1, the trip would take about 27 million years. 27 million years. That is about 90 times longer than Homo sapiens have existed. 27 million years ago, Earth was in the Oligocene epoch. Grasslands were spreading. Early apes were beginning to appear. Whales had already become ocean animals. The continents were still moving into the shapes we know today. The world was alive, changing, and completely empty of humans. A Voyager speed journey to the nearest known black hole would need that kind of time. And Voyager is the emotional symbol of deep space travel. It carries a golden record with sounds and images from Earth. It carries greetings in dozens of human languages. It carries the sound of wind, thunder, birds, footsteps, heartbeats, and music. It is humanity's message in a bottle. And still, by the standards of interstellar travel, it is drifting slowly. This is the brutal lesson of Voyager. A spacecraft can survive for decades. It can cross the boundary into interstellar space. It can become the most distant human object ever made. And it can still be nowhere close to reaching another star system, let alone a black hole. So the comparison has to become more extreme. If Voyager is too slow, then we need the fastest machine humanity has ever built. Voyager gives us distance, but Parker Solar Probe gives us speed. Parker Solar Probe launched on August 12, 2018, from Cape Canaveral in Florida. Its mission was to study the Sun closer than any spacecraft before it. The Sun is not a solid surface. It is a massive ball of plasma, which means gas so hot that atoms are stripped apart into charged particles. Around it is the corona, the outer atmosphere of the Sun, where temperatures can reach millions of degrees. Parker was built to fly through that environment. To survive, it carries a thick carbon composite heat shield. The shield is about 4.5 inches thick. During close approaches, the side facing the Sun can heat to around 2,500 degrees Fahrenheit. But behind that shield, the instruments remain protected enough to keep working. Parker does not carry humans. It does not carry food. It does not carry water. It does not carry a cabin, windows, beds, exercise equipment, or life support. It is a compact machine built around instruments, shielding, antennas, and systems that can tolerate brutal sunlight. That matters because Parker's speed record comes from a very special path. It is not cruising through empty interstellar space with engines burning steadily behind it. It is falling deep into the Sun's gravity well. A gravity well is the invisible downhill slope created by a massive object's gravity. The closer something falls toward the Sun, the faster it moves, the same way a stone speeds up as it falls toward Earth. Parker also uses repeated flybys of Venus. A flyby is when a spacecraft passes close to a planet and uses the planet's gravity to reshape its orbit. Parker uses Venus to tighten its path around the Sun, bringing each close solar pass deeper than the last. On its closest approaches, Parker Solar Probe reaches about 430,000 miles per hour. That is faster than any human-made object has ever moved. At that speed, it could travel from Earth to the Moon in a little over half an hour. It could cross the width of the United States in less than 30 seconds. It could circle Earth in about 3.5 minutes. By every ordinary human standard, that speed feels almost unreal. And yet, Gaia BH1 is still roughly 2.4 million years away at Parker speed. 2.4 million years. That is older than our species, older than agriculture, older than language as we know it, older than every city, every road, every book, every telescope, and every rocket ever built. 2.4 million years ago, early members of the genus Homo were living in Africa. Stone tools already existed. The world was entering the Pleistocene epoch, a long age of shifting ice sheets, changing climates, and migrating animals. Mammoths, saber-toothed cats, giant ground sloths, and early human relatives would all belong to that deep chapter of Earth's story. A spacecraft moving at the fastest speed humanity has ever achieved would need that kind of time to reach the nearest known black hole. And even that comparison gives Parker too much credit. Parker reaches its record speed only near the Sun. Far from the Sun, on the outer part of its stretched orbit, it moves much more slowly. Its entire speed record is tied to the thing it is falling around. A black hole mission cannot borrow that same solar plunge for 1,560 light years. Once a spacecraft leaves the solar system, the Sun becomes a distant star behind it. The gravity that made Parker so fast fades into the background. the heat shield that protects Parker near the Sun becomes almost irrelevant in the cold space between stars. And the spacecraft itself has no plan for carrying people, no plan for slowing down at another star system, and no plan for surviving millions of years as an active machine. So Parker teaches us something important. Humanity can make a machine move unbelievably fast. We can aim it into the inner solar system. We can protect it from temperatures that would melt many metals. We can use gravity assists with Venus to tighten its path until it dives closer and closer to the Sun. But even the fastest machine ever built turns the trip to Gaia BH1 into a journey longer than the entire human story. Current technology has now failed in every form. Human speed failed. Living orbital speed failed. Deep space probe speed failed. Even the fastest solar probe failed. So the journey has to leave today's machines behind. To make the nearest black hole feel even remotely reachable, the spacecraft has to move at a fraction of the speed of light. So let's leave today's spacecraft behind. Let's imagine something far beyond Apollo, far beyond the International Space Station, far beyond Voyager, far beyond Parker's solar probe. A ship moving at 1% of the speed of light. Light moves at about 186,000 miles per second. 1% of that is about 1,860 miles per second. That is roughly 6.7 million miles per hour. This is the kind of speed where normal human comparisons begin to fail. At 1% light speed, you could travel from Earth to the Moon in a little over 2 minutes. You could cross the distance from Earth to the Sun in less than 14 hours. You could reach Mars at a close approach in about 5 hours. You could reach Jupiter in a few days. The entire solar system would start to feel smaller. A trip that once took spacecraft years could shrink to days or weeks. This is the first speed that sounds like it belongs to interstellar travel. But we have never built anything close to it. Parker's solar probe reaches about 430,000 miles per hour near the Sun. 1% light speed is more than 15 times faster than that. And Parker is already the fastest human-made object ever recorded. A human ship at 1% light speed would need a propulsion system unlike anything we currently operate. Chemical rockets would be far too weak. Ion engines would be too slow. Nuclear propulsion might help, but even that would require engineering far beyond today's spacecraft. Fusion drives are one possible idea. Fusion is the process that powers the Sun. It happens when light atoms, usually forms of hydrogen, combine into heavier atoms and release energy. On Earth, scientists have studied fusion for decades because it could provide enormous amounts of power. But a working fusion power plant is already difficult. A compact fusion engine that can push a spacecraft across interstellar space is a much larger challenge. Another idea is a laser sail. A huge laser array near Earth or in space could fire light at a thin reflective sail. Light has momentum, which means it can push, even though each photon has no rest mass. If the sail were light enough, and the beam powerful enough, the spacecraft could gradually accelerate to a meaningful fraction of light speed. The problem is scale. The sail would need to be extremely thin. The beam would need to stay focused across huge distances. The spacecraft would need to survive acceleration, dust impacts, and the long silence after the laser stops pushing. So 1% light speed already requires technology that sits far beyond our normal space program. And even at that speed, Gaia BH1 is still about 156,000 years away. That number changes the feeling of the mission again. 156,000 years is far longer than recorded civilization. Writing began around 5,000 years ago in places like ancient Sumer and Egypt. The earliest cities formed along rivers like the Nile, the Tigris, the Euphrates, the Indus, and the Yellow River. Agriculture began roughly 10,000 to 12,000 years ago, when humans started planting crops like wheat, barley, rice, and millet instead of only hunting and gathering. The oldest known cave paintings are older than that. Some paintings in Europe and Indonesia are tens of thousands of years old. But 156,000 years reaches far deeper. It stretches back toward a time when modern humans existed, but civilization did not. No cities, no written language, no metal tools, no farms, no wheels, no sailing ships, no calendars, no telescopes, no nations. At 1% light speed, a spacecraft leaving Earth in 2026 would need a journey longer than the entire path from early human prehistory to the modern world. A civilization could rise, split into languages, build monuments, invent science, enter space, and vanish from memory while the ship was still traveling. That is the strange cruelty of 1% light speed. It feels futuristic. It feels impossible by today's standards. It would make the planets feel close. And still, against the distance to the nearest known black hole, it becomes a prehistoric to future journey. So the speed has to climb again. The ship has to move faster than anything humans have built, faster than anything humans have seriously tested, and fast enough that space itself begins to become dangerous in new ways. So let's push the ship much faster. Not 1% of light speed, 10%. At 10% of light speed, a spacecraft would be moving at about 18,600 miles every second. That is about 67 million miles per hour. At that speed, Earth to the Moon would take about 13 seconds. Earth to the Sun would take about 1 hour and 20 minutes. A trip to Neptune, the farthest major planet, could take less than 2 days if the path were direct. The solar system would shrink from a place of years into a place of hours and days. This is the first speed where the nearest black hole begins to sound reachable. Gaia BH1 is about 1,560 light years away. At 10% of light speed, the journey would take about 15,600 years. That is a huge improvement over millions of years. But 15,600 years is still longer than all recorded human history several times over. Writing began around 5,000 years ago. The first known writing systems appeared in Mesopotamia and Egypt, carved into clay tablets, painted on walls, and pressed into symbols for grain, taxes, names, kings, and trade. The pyramids of Egypt were built about 4,500 years ago. Stonehenge was raised in stages around the same deep period of human history. The Roman Empire rose and fell in the last 2,000 years. The first telescopes were pointed at the sky only about 400 years ago. The first airplane flew in 1903. The first satellite reached orbit in 1957. The first human walked on the moon in 1969. All of that fits easily inside 5,000 years of recorded civilization. A 10% light speed journey to Gaia BH1 would take more than 3 times that span. A ship leaving in 2026 would arrive around the year 17,626. By then, every nation on Earth could be gone or transformed beyond recognition. Every language spoken today could have changed into something unfamiliar. Every building now standing could be dust, buried, rebuilt, or preserved only as an ancient site. At this speed, the mission finally becomes short enough to imagine. But it is still too long for a person. It is too long for a normal crew. It is too long for a single government, a single culture, or a single generation of technology. And 10% light speed brings a new problem. The faster you move, the more dangerous empty space becomes. Interstellar space feels empty because the gas between stars is incredibly thin. In the space around the Sun, once you are beyond the heliosphere, there may be around 1 atom in a small cube of space the size of a sugar cube. Most of that material is hydrogen, the simplest element in the universe. There are also helium atoms, charged particles, magnetic fields, cosmic rays, and tiny grains of dust made from carbon, silicates, ice, and material shed by old stars. At low speed, a hydrogen atom hitting a spacecraft is almost meaningless. At 10% light speed, even small things arrive with serious energy. The reason is kinetic energy. Kinetic energy is the energy of motion. If you double speed, the impact energy does more than double. It rises with the square of velocity. That means speed makes collisions much more dangerous very quickly. A dust grain smaller than a speck of smoke could hit like a microscopic bullet. A larger grain could punch into shielding, vaporize material, and send a spray of hot particles into the spacecraft's forward layers. A ship, traveling for 15,600 years, would need to face that risk again and again. The front of the spacecraft could need a thick shield. Maybe layers of metal, ceramic, water, ice, or other material placed ahead of the living sections. Some designs imagine a large sacrificial shield flying far in front of the ship. Others imagine magnetic fields to deflect charged particles. But magnetic fields cannot push aside ordinary neutral dust. And every shield adds mass. Every extra ton makes acceleration harder. Every extra ton makes slowing down harder. So 10% light speed creates the first version of the journey that feels almost possible. Then it immediately becomes a survival problem. The ship cannot simply be fast. It has to be durable for thousands of years. It has to carry protection, power, repair systems, and people who will never personally see the destination. At this speed, the journey to the nearest known black hole stops being a trip. It becomes a civilization moving through the dark. At 10% of light speed, the journey finally becomes short enough to imagine. But 15,600 years is still far too long for a normal spacecraft. A normal spacecraft is built for a mission, a launch, a route, a crew, a destination. This would need to be something larger. It would need to be a world in motion. For 15,600 years, the ship would have to carry a small piece of Earth inside it. Air could not simply be stored in tanks. Water could not simply be packed in containers. Food could not simply be loaded before launch. Every breath, every meal, every shower, every repair, every birth, every death, and every emergency would happen inside the same sealed system. A sealed system means the ship must reuse almost everything. The International Space Station already does part of this. Its life support system recycles water from humidity, sweat, and urine. It removes carbon dioxide from the air. It produces oxygen, partly by using electricity to split water into hydrogen and oxygen. That process is called electrolysis. But the station still depends on regular cargo deliveries from Earth. A generation ship to Gaia BH1 would have no cargo deliveries, no spare shipment arriving next month, no emergency capsule, no quick return. The ship would need a closed ecosystem. An ecosystem is the web of living and non-living systems that keep life going. On Earth, forests, oceans, soil, bacteria, plants, animals, rain, sunlight, and the atmosphere all work together. On the ship, that whole chain would need to be rebuilt artificially. Plants would be essential. Hydroponics could grow crops without soil, using water mixed with minerals. Aeroponics could grow roots in mist. Algae tanks could help produce oxygen and protein. Yeast, fungi, and bacteria could recycle waste and create useful nutrients. Nothing could be treated as garbage in the ordinary sense. Human waste would become fertilizer. Carbon dioxide from breathing would become plant food. Plant waste would become compost, animal feed, or chemical feedstock. Water from washing, cooking, breathing, and urine would be filtered and used again. Even a tiny loss rate becomes dangerous over thousands of years. If the ship lost just a small fraction of its water each year, the missing amount would grow into a fatal shortage over deep time. Food would be just as difficult. 100 people need hundreds of thousands of calories every day as a group. 1,000 people need millions. The ship would need farms under artificial light. Rows of wheat, rice, potatoes, beans, lettuce, tomatoes, algae, and possibly aquaculture tanks with fish. Every crop would need seeds. Every seed bank would need protection. Every growing chamber would need backups in case of mold, pests, disease, or mechanical failure. Earth has already shown how hard this is. In 1991, the Biosphere 2 experiment in Arizona sealed 8 people inside a glass habitat for 2 years. It had a rainforest, ocean, desert, farm, and living quarters. Even with Earth right outside, the system struggled. Oxygen levels dropped. Food production was difficult. The crew lost weight. That was 2 years. This ship would need to work for 15,600. Gravity becomes another problem. Without gravity, bones weaken and muscles shrink. Astronauts in orbit exercise for hours each day to slow the damage. For a voyage this long, the ship would likely need artificial gravity. The most realistic method is rotation. If part of the ship spins, people inside feel pushed outward against the floor. A huge rotating ring could create something like gravity. But the ring would need to be large. If it spins too fast, the crew would feel strange sideways forces when they move their heads or walk across the floor. That effect is called the Coriolis effect. It can cause dizziness, nausea, and disorientation. So the habitat might need to be hundreds of feet wide, perhaps much larger, to spin slowly enough for people to live normally. Power would have to be constant. Solar panels would fade into uselessness once the ship moved far from our star. A nuclear reactor could provide power for years or decades. For thousands of years, the ship would need replaceable reactor parts, fuel reserves, or a working fusion system. Fusion is the process that powers stars, where light atoms combine and release energy. If humans ever learned to build compact fusion engines, they could provide both propulsion and long-term power. But the ship would still need radiators. Radiators are large panels that release waste heat into space. In a vacuum, heat cannot drift away into air. It has to be carried to the surface and radiated out as infrared light. Even the repair systems would have to become industrial. The crew would need machine shops, 3D printers, metal recycling, electronics fabrication, medical labs, spare parts for parts that make other spare parts. Over 15,600 years, every original component would eventually become ancient. The ship would survive only if it could keep rebuilding itself. At that point, the spacecraft has become a settlement, a traveling city sealed inside metal, water, glass, soil, roots, machines, and memory. And once the ship becomes a world, the journey depends on people who will never see where it began. A ship like this changes the meaning of departure. The first crew would leave Earth with training, purpose, and a destination. They would know the name Gaia BH1. They would know the distance. They would know the black hole was waiting in the direction of Ophiuchus. But they would also know something much harder. They would never see it. At 10% of light speed, the journey still takes about 15,600 years. A healthy human life might last 80 or 90 years. A very long life might pass 100. Even if the first crew lived unusually long lives, they would experience less than 1% of the voyage. They would be the launch generation. The people who remembered Earth directly. They would remember real rain, real oceans, real wind moving through trees, real gravity pulling evenly through the body. They would remember sunsets that happened once per day instead of on a schedule made by rotating habitat lights. But the ship would continue long after them. Their children would inherit the corridors, farms, schools, engines, water systems, and sealed metal walls. Their grandchildren would inherit the same mission. Then their descendants. Then the descendants of those descendants. If each generation averaged about 25 years, a 15,600-year journey would pass through more than 600 generations. That is an almost impossible human chain. 600 generations ago on Earth, there were no cities, no writing, no farms, no nations. Human beings were hunter-gatherers, moving through landscapes of ice, grassland, forest, and coast. The people living then could never have imagined satellites, antibiotics, airplanes, telescopes, or a spacecraft aimed at a black hole. And yet, a mission to Gaia BH1 would need a society to remain focused across a similar depth of time. The original crew could write instructions. They could record messages. They could build schools into the ship's culture. They could teach children why the vessel exists. They could mark the distance traveled each year. they could preserve star charts, mission logs, engineering manuals, and stories of Earth. But over thousands of years, information has to do more than survive. It has to matter. A technical manual can sit in an archive. A mission can fade inside the people meant to carry it. The destination would need to become part of daily life. Children might learn the name Gaia BH1 before they learn the names of ancient countries on Earth. They might celebrate launch day every year. They might keep portraits of the first crew in a central hall. They might recite the distance already crossed and the distance still ahead. They might treat the navigation room the way older civilizations treated temples, courts, or royal archives. The mission would need law, because memory alone weakens. A future generation might ask why they must keep traveling, why they must maintain engines they did not choose, why they must ration water for a black hole no one alive has seen, why they must live inside a ship because of a decision made by ancestors thousands of years earlier. So the mission would need rules written into the structure of society. Education would train engineers, doctors, farmers, teachers, pilots, historians, and repair crews. Children would learn how air is recycled, how algae tanks work, how crops are pollinated under artificial light, how rotating gravity depends on careful balance, how radiation shielding protects the living decks, how navigation must account for moving stars. A mistake in one generation could become a disaster for all later generations. A neglected pipe, a corrupted archive, a broken pump, a failed crop strain, a political conflict that splits the crew. A generation ship cannot depend on heroism once every few centuries. It needs ordinary competence repeated every day by people who were born into the mission. That may be the deepest human cost of the journey. The first crew chooses to leave. Their descendants inherit the result. By the time Gaia BH1 finally grows from a coordinate into a real system ahead of them, the people aboard may have no memory of Earth as home. They may know Earth as origin, as history, as a blue world in old recordings, as the place their ancestors left before the ship became their whole universe. And that changes the journey again. It is no longer a mission carried by astronauts. It is a civilization asking its children to keep moving toward a destination chosen before they existed. The first children born on the ship would inherit a strange kind of normal. They would wake beneath artificial lights. They would sleep beside humming ventilation ducts. They would learn the sound of pumps, fans, motors, and rotating machinery before they ever heard waves on a shore. To them, the ship would feel like home because it would be the only home they had ever touched. They would know floors that curved gently with the shape of the rotating habitat. They would know farms arranged in trays, stacked under grow lights. They would know water as something counted, filtered, measured, and returned to the system. They would know air as something maintained by machines, plants, algae tanks, scrubbers, sensors, and careful human attention. But they would never stand under an open sky. They would never feel natural wind moving across a field. They would never see clouds forming over an ocean. They would never hear real rain striking leaves, roads, rooftops, or soil. They would know forests through recordings. A redwood forest in California, with trees more than 300 feet tall. The Amazon rainforest, where billions of leaves release water vapor back into the air, the boreal forests of Canada and Siberia, stretching across cold northern land for thousands of miles. They would know oceans through old images. The Pacific, covering more area than all land on Earth combined. The Atlantic, crossed by ships for centuries. The Indian Ocean, warmed by monsoons and bordered by Africa, Asia, and Australia. They would know weather as a lesson. Thunderstorms would become videos in a classroom. Snow would become a chemical and historical concept. Hurricanes would become rotating storms explained by warm ocean water, rising air, and the Coriolis effect, the sideways turning caused by a spinning planet. Earth would become an archive. Maps, languages, photographs, old films, recorded voices, satellite images, music, birdsong, whale calls, the sound of insects at night, the sound of human crowds in cities that may no longer exist by the time the ship is halfway to Gaia BH1. A child might learn that Earth had blue oceans, white ice caps, deserts, coral reefs, grasslands, mountain ranges, and cities bright enough to glow from orbit. But all of it would come through screens, lessons, stories, and preserved memory. The word home would begin to change. For the first generation, home would mean Earth. For the second generation, home might mean Earth and ship together. After 100 generations, Earth could feel like an origin story. After 600 generations, it might feel almost mythic. Real but distant. Sacred but unreachable. The ship would have its own places. The orchard deck, the water recycling level, the school ring, the navigation chamber, the engine spine, the old crew memorial, the shielded storm shelter where people gather during radiation events. Children would grow up naming those places the way children on Earth name streets, rivers, parks, and neighborhoods. Their identity would slowly shift. They would still be human. Their bodies would still carry Earth biology, calcium in their bones, iron in their blood, DNA shaped by billions of years of evolution on one planet. But culturally, they would become something new. People of the ship. People whose ancestors left Earth. People born between stars. Their calendars might count years since launch. Their holidays might mark the first crossing of the Oort cloud, the first century in interstellar space, the halfway point to Gaia BH1. Their art might show Earth as a blue circle, and the black hole as a dark destination wrapped in bent starlight. Their songs might use the rhythm of machinery. Their myths might come from alarms, repairs, crop failures, course corrections, and stories of the first crew. And with every generation, the same pressure would return. Why keep going? Why maintain a promise made thousands of years earlier? Why spend a life protecting engines, farms, water tanks, and archives for a destination no living person chose? A society like that cannot survive on memory alone. It needs trust. It needs law. It needs leadership that can last longer than any empire Earth has ever known. A ship that lasts 15,600 years cannot be governed like a normal mission. A normal mission has a commander, a crew, a checklist, a control room on Earth, a launch date, and a return plan. This ship would need a civilization. It would need laws for people born centuries after launch. It would need courts or councils to settle disputes. It would need rules for food, water, space, medicine, work, education, reproduction, punishment, leadership, and emergency power. Every person aboard would live inside a shared machine. That changes what freedom means. On Earth, one household can waste water, and the ocean remains outside. On the ship, wasted water belongs to everyone. A damaged airlock belongs to everyone. A broken crop chamber belongs to everyone. A sick reactor belongs to everyone. The ship would need resource laws as strict as physics. How many liters of water can each person use per day? How many calories can be stored in reserve? How many square feet of growing space each crop receives? How many children the population can support? How much oxygen must remain in backup tanks? How many spare filters, pumps, valves, and circuit boards must be protected at all times? Even reproduction becomes part of survival planning. On Earth, population growth can spread into new cities, farms, and territories. On a ship, population growth runs into walls. Too few children, and the society ages, shrinks, and loses skills. Too many children, and the ship may strain its food, air, water, school systems, medical care, and living space. The society would need to keep enough genetic diversity to avoid inherited health problems over hundreds of generations. It would need family records, medical records, and perhaps careful population planning. That is a cold thing to imagine. But a closed world cannot ignore biology. Education would become one of the most important survival systems. Children would need history, reading, mathematics, medicine, engineering, agriculture, physics, chemistry, navigation, and conflict resolution. They would need to understand why algae tanks matter, why carbon dioxide scrubbers matter, why radiation shelters matter, why rotating gravity must stay balanced, why one damaged bearing in a habitat ring can threaten thousands of lives. A school on this ship would be more than a place for learning. It would be how the mission repairs itself through each new generation. Small failures would carry enormous weight. A fungus spreading through a wheat crop could reduce food reserves. A leak in a water line could become a crisis if sensors miss it. A coolant failure near a reactor could force parts of the ship to shut down. A computer archive damaged by radiation could erase instructions for old machinery. A disease could move quickly through a closed population, breathing the same recycled air. Even social trust would be a life support system. A rumor could become panic. A leadership dispute could delay repairs. A shortage could divide families. A generation that stops believing in the mission could neglect systems built for people thousands of years ahead. Earth gives us warning signs. The old kingdom of Egypt lasted for centuries. The Roman Empire in the West lasted about 500 years. The Han dynasty in China lasted about 4 centuries. The Indus Valley civilization flourished for many centuries before its cities changed and declined. These were among the great long-lived societies of Earth. A ship to Gaia BH1 would need stability across 15,600 years, longer than any empire, longer than any modern nation, longer than written history itself. And it would have no outside wilderness to retreat into, no neighboring country to trade with, no ocean to cross, no new continent to settle, no rescue force arriving from beyond the horizon. The hull would be the border of the world. Beyond it would be vacuum, radiation, dust, and darkness. So the ship would need emergency authority, clear rules for who takes command during fire, crop failure, reactor trouble, epidemic illness, navigation errors, or structural damage. The system would have to be strong enough to act quickly and trusted enough that emergency power does not become permanent rule. That balance is hard even on Earth. Inside a sealed vessel moving between stars, it becomes part of survival. A civilization like this could endure only if its people believed the ship belonged to them, their farms, their laws, their dead, their future, their destination. But even if the ship holds together inside, Earth would keep falling farther behind, and eventually the home world would become less like a partner and more like a distant voice arriving from another age. At first, Earth would still feel close. In the early days after launch, a message from mission control might take seconds or minutes to arrive. That is familiar spaceflight. Apollo astronauts heard voices from Houston while they crossed the distance to the Moon. The International Space Station speaks with ground stations every day. Even Voyager 1, more than 15 billion miles from Earth, still receives commands through the Deep Space Network. But a mission to Gaia BH1 would slowly leave that kind of connection behind. Radio signals travel at the speed of light. So do laser signals. That means no message can cross space faster than light itself. At 1 light year from Earth, a message takes 1 year to arrive. At 10 light years, it takes 10 years. At 100 light years, it takes a century. Gaia BH1 is about 1,560 light years away. Near the end of the journey, a message from Earth would take 1,560 years to reach the ship. A reply would take the same amount of time to come back. One exchange would take more than 3,000 years. Someone near Gaia BH1 could send a message home saying the ship had arrived. Earth would receive it 15 centuries later. Then Earth could answer. And that answer would not reach the ship for another 15 centuries. The full reply loop would be longer than the time between ancient Greece and the modern world. Longer than the time between the Roman Empire and the first rockets. Longer than the entire history of English as a recognizable language. Communication would become something stranger than conversation. It would become archaeology moving at light speed. A message from Earth might arrive filled with the language, politics, fears, and hopes of people who had been gone for more than 1,000 years. A greeting recorded by one generation would be heard by descendants who lived 50 or 60 generations later. A warning might arrive after the danger had passed. An instruction might arrive after the machine it described had been replaced. A celebration might arrive after the people being honored were ancient names in the ship's archive. Even in the middle of the journey, the delay would reshape the relationship. At 500 light years out, Earth is 500 years away by signal. The ship could ask for help with a reactor design. The answer would come 1,000 years after the problem was first reported. By then, the crew would have solved it, failed to solve it, or changed the system entirely. The people who asked would be long gone. Their descendants might read the answer as history, maybe useful history, maybe sacred history, may be just another message from a planet they know only through lessons. The same thing would happen in reverse. Earth would receive updates from people who had lived centuries earlier aboard the ship. A child might be born, trained, work an entire lifetime, and die before Earth even learned their name. A political crisis aboard the ship could be over for generations before Earth heard the first report. A crop failure, a disease outbreak, a course correction, a new law, a birth, a death, a discovery. All of it would arrive late, always late. And Earth itself would change while those messages were traveling. In 1,560 years, languages can split, religions can transform, governments can vanish, coastlines can shift, cities can be abandoned, rebuilt, renamed, or buried. The Earth that sent a message may no longer exist in the same form by the time the message is received. So the ship would slowly become independent by force. Earth could still speak. Earth could still listen. But it could no longer guide the mission in any immediate way. There would be no real-time command, no emergency help, no shared present, only records crossing the dark. The people aboard would live with Earth as a delayed presence, a voice from behind them, a blue world shrinking into history, a place that sends messages from another age. And after enough centuries, even Earth's memory of the ship could begin to weaken. 15,600 years is long enough for a mission to change shape inside memory. On Earth, almost everything humans build changes across that kind of time. Languages drift. Words soften, split, disappear, and return with new meanings. The English spoken 1,000 years ago already sounds like a different language to most modern listeners. Latin became Spanish, French, Italian, Portuguese, Romanian, and other related languages. Ancient Egyptian changed across thousands of years before it faded from daily speech. Sumerian, one of the earliest written languages, survived in records long after people stopped using it as a living language. A mission to Gaia. BH1 would have to cross a span of time much longer than the full written history of those languages. By the time the ship neared its destination, the language spoken at launch could be preserved mostly in ceremony, archives, or translation. The original mission recordings might sound ancient. The first crew's voices might need subtitles. Their jokes, accents, idioms, and emotional references might feel distant to their own descendants. Governments would change too. 15,600 years is longer than the time between the first known city-states and the present day. Uruk, one of the great cities of ancient Mesopotamia, flourished more than 5,000 years ago. The old kingdom of Egypt rose more than 4,500 years ago. The Roman Republic, the Han dynasty, the Maya city-states, the Abbasid Caliphate, the Mongol Empire, the British Empire, and every modern nation all fit inside a much smaller window of history. A ship leaving in 2026 could arrive after Earth had passed through political forms we cannot name yet. New countries, new unions, new collapses, new maps, new borders, new systems of rule. Even religion and mythology could change around the mission. At launch, the trip might be seen as science, a carefully calculated expedition toward the nearest known black hole. Thousands of years later, people on Earth might remember it differently. A sacred departure, a warning story, a heroic founding myth, a symbol of human ambition, a mistake from an earlier age, or a half-forgotten legend about ancestors who flew into the dark. The same could happen aboard the ship. The first crew might be remembered as engineers and astronauts, then as founders, then as almost mythic figures. Their names could be painted in schools, carved into memorial walls, spoken during annual ceremonies, or attached to habitat rings and agricultural decks. A water recycling chamber might be named after the engineer who repaired it during the 1st century. A navigation ritual might begin as a practical systems check and slowly become tradition. A launch day briefing could become a yearly recitation. History has a way of becoming ceremony when people need it to hold a society together. Technology could also move beyond recognition. Earth in the year 17,626 might have propulsion systems, energy sources, medicine, computers, and biological tools that would seem impossible to the launch generation. Or Earth might have lost capabilities. Wars, climate shifts, asteroid impacts, artificial disasters, pandemics, social collapse, or simple decline could erase the institutions that supported the mission. The planet might still know the ship exists. It might track it with enormous telescopes and beam messages across the dark. It might send faster missions that overtake it. It might abandon the project completely. It might lose the records. It might remember the ship only as an old story from a vanished civilization. And the ship could preserve a version of Earth that Earth itself has outgrown. Inside its archives, Earth might remain a planet of 21st century coastlines, nations, languages, music, forests, cities, and families. The ship might carry recordings of New York, Lagos, Tokyo, Cairo, Toronto, Mumbai, Sao Paulo, and London as they looked before launch. It might carry maps of glaciers that later melted, coastlines that later shifted, species that later disappeared, voices of people whose descendants no longer know their names. The ship could become a museum of a planet that kept changing after it left. That is the quiet loneliness of deep time travel. The crew loses Earth through distance. Earth loses the crew through time. And between them, the mission becomes something neither side fully controls anymore. A machine can keep moving through space. A society can keep teaching its children where it is going. A planet can keep sending messages into the dark. But after 15,600 years, the journey has become culturally isolated as well as physically isolated. And outside the hull, beyond the farms, schools, archives, laws, and memories, the space between stars is still waiting. Outside the hull, interstellar space would look calm. No planets nearby. No sunlight bright enough to warm the ship. No clouds, storms, oceans, or weather. Just stars, darkness, and distance. But the space between stars is still a physical environment. It contains gas. It contains dust. It contains plasma. It contains magnetic fields. It contains cosmic rays. And at 10% of light speed, even thin space becomes something the ship has to survive. The gas between stars is called the interstellar medium. Medium just means material that fills a region. In this case, the material is extremely thin. Near our part of the galaxy, there may be less than 1 atom in a cubic centimeter of space. A cubic centimeter is about the size of a sugar cube. The air at sea level on Earth contains tens of billions of molecules in that same volume. So by Earth standards, interstellar space is an incredible vacuum. But across 15,600 years, tiny amounts of matter still add up. Most of that gas is hydrogen. Hydrogen is the simplest element in the universe. 1 proton, 1 electron. There is also helium, traces of heavier elements, and regions of plasma. Plasma is gas that has been energized so much that electrons are stripped away from atoms. The sun is made of plasma. Lightning is plasma. The solar wind is plasma. And the galaxy has plasma spread through the space between stars. At slow speeds, a spacecraft can pass through this material with very little trouble. Voyager 1 is moving through interstellar space at roughly 38,000 miles per hour. At that speed, individual atoms barely matter. But a ship, moving at 10% light speed, is traveling about 18,600 miles every second. At that speed, the ship is sweeping through space like a needle moving through an invisible storm. Hydrogen atoms would strike the forward shield constantly. Each atom is tiny, but the number of impacts would be enormous. Over years, centuries, and millennia, those impacts could heat the forward surface, damage materials, and slowly weaken exposed structures. Then there is dust. Interstellar dust grains are small pieces of matter made from silicates, carbon, ice, and metals. Many are born in the outer layers of dying stars. Some are scattered by supernova explosions. Some drift inside cold molecular clouds where new stars are forming. A dust grain can be smaller than smoke. A larger grain might be the size of a bacterium, a pollen grain, or a speck of fine sand. At 10% light speed, that is enough to matter. The danger comes from kinetic energy. Kinetic energy is the energy of motion. When speed increases, impact energy rises very quickly. Double the speed and the impact energy becomes 4 times greater. Increase the speed by 100 and the energy becomes 10,000 times greater. So a tiny dust grain at 10% light speed can hit like a concentrated projectile. It could pit a shield, damage a sensor, punch into a radiator, vaporize a small patch of material, or send a spray of hot particles into the layers behind it. The ship would need a forward shield, maybe thick layers of metal and ceramic, maybe tanks of water or ice placed ahead of living areas. Water is useful because it can absorb radiation and also serve as a life support reserve. Some designs imagine a separate shield flying ahead of the main ship, taking the first impacts before debris reaches the habitat. But shields are heavy. Radiation creates the same problem. Cosmic rays are high-energy particles, mostly protons, moving through the galaxy at extreme speeds. Many are accelerated by supernova remnants, the expanding shock waves left after massive stars explode. Earth is protected by its atmosphere and magnetic field. A ship between stars has to bring its own protection. Thick shielding can reduce radiation exposure. Water, plastics rich in hydrogen, and layers of material around sleeping quarters could help. The crew might also need storm shelters, small protected rooms where people gather during periods of high radiation. But every kilogram of shielding has to be accelerated. Every kilogram has to be carried for 15,600 years. And if the ship plans to stop near Gaia BH1, every kilogram also has to be slowed down. Protection keeps the civilization alive. Mass makes the journey harder. The ship survives by becoming heavier. And the heavier it becomes, the more difficult it is to send toward the black hole in the first place. Reaching Gaia BH1 is only half the journey. The ship also has to arrive slowly enough to stay. At 10% of light speed, the spacecraft is moving about 18,600 miles every second. That is fast enough to cross Earth's diameter in less than 1 second. Fast enough to pass the Moon in about 13 seconds. Fast enough to fly through the inner solar system before anyone aboard could meaningfully react. If the ship reaches the Gaia BH1 system at that speed and does nothing, it does not arrive in the way humans usually imagine arrival. It flashes through. It becomes a flyby. After 15,600 years of travel, the black hole system could pass by in a brief scientific blur. A few measurements. A narrow window of images. Then the ship keeps going into deeper space, still carrying the speed it built across centuries or millennia. To stay near Gaia BH1, the ship has to slow down. And slowing down in space is not like braking a car. A car slows because its tires push against the road. An airplane slows because air presses against its wings and body. In deep space, there is no road. There is almost no air. A spacecraft changes speed by throwing mass or energy in the opposite direction. That means fuel. If the ship used engines to accelerate to 10% of light speed, it may need engines again to cancel that speed before arrival. In simple terms, it has to spend energy twice. Once to leave, once to stay. This is where the mass problem becomes brutal. Fuel has mass. Tanks have mass. Engines have mass. Radiators have mass. Shielding has mass. And if you carry fuel for slowing down, you must accelerate that fuel during the first half of the mission. Then you must carry it for thousands of years. Every extra kilogram added for arrival makes departure harder. This is part of what engineers call the rocket equation. The rocket equation describes how much propellant a spacecraft needs to change its speed. It has a cruel shape. Adding more payload means adding more fuel. Adding more fuel means adding more mass. That extra mass then needs even more fuel to move. For a small probe, this is difficult. For a generation ship with farms, water, shielding, people, reactors, spare parts, and rotating habitats, it becomes one of the central obstacles of the entire mission. A fusion engine could help if humans learned how to build one. Fusion is the process that powers stars, where light atoms combine and release energy. A fusion-powered starship might use hydrogen isotopes as fuel and release far more energy than chemical rockets. It could spend years or centuries gradually slowing the ship as Gaia BH1 approached. But the engine would have to survive. Its magnets, fuel systems, nozzles, computers, and cooling systems would need repair across hundreds of generations. A magnetic sail is another idea. A magnetic sail would create a huge magnetic field around the ship. Charged particles from a star or from thin interstellar plasma, could push against that field and create drag. Drag means resistance that slows motion. A normal sail catches wind. A magnetic sail catches charged particles. Near Gaia BH1, the visible companion star could provide some stellar wind. Stellar wind is a stream of charged particles flowing outward from a star. But the ship would need to deploy the magnetic sail at exactly the right time, with the right orientation, across enormous distances. Too early, and the mission loses speed before reaching the target. Too late, and the ship misses its chance to slow down. The companion star's light could also be used in theory. A large reflective sail could turn toward the star and let incoming light push against it. Light pressure is weak, but over time it can matter. The challenge is size. A sail large enough to slow a massive generation ship would be enormous. It would need to unfold after thousands of years, survive dust damage, hold its shape, and point with extraordinary precision. The ship could also use the gravity of the companion star. By passing close at the right angle, it could bend its path and trade some speed. This is called a gravity assist. Voyager used gravity assists from Jupiter and Saturn. Parker Solar Probe uses Venus to reshape its orbit around the Sun. But Gaia BH1 would demand far greater precision. The ship would be arriving after 15,600 years. The star would be moving. The black hole would be moving. The ship would be moving at a fraction of light speed. A tiny navigation error made centuries earlier could become millions or billions of miles by arrival. After all that time, the ship could reach the correct region of the galaxy and still fail to arrive. It could pass the hidden black hole like a needle through darkness. Survival requires speed. Discovery requires slowing down. And somewhere ahead, the destination itself may be almost invisible. After thousands of years of travel, the ship would finally enter the region of Gaia BH1. But the destination would not look like a planet. It would not look like a star. It would not glow like a lighthouse ahead of the ship. A quiet black hole can be almost completely dark. A black hole has no solid surface. It has no glowing crust. It has no atmosphere in the ordinary sense. If gas is falling into it, that gas can heat up and shine brightly. Some black holes are surrounded by blazing disks of material called accretion disks. Accretion means matter gathering inward under gravity. As gas spirals closer, friction and compression heat it to extreme temperatures. That hot gas can release X-rays, ultraviolet light, and visible glow. Gaia BH1 appears much quieter than that. It is known because something visible is moving around it. The key object is its companion star. Gaia BH1 is a binary system. Binary means two objects bound together by gravity. In this case, one object is a normal star, similar in some ways to the Sun. The other object is a black hole with roughly 10 times the mass of the Sun. The two objects orbit a shared center of mass. That center is the balance point of their motion. A small child and an adult spinning while holding hands do something similar. Both move around a shared point, though the heavier person moves less. In Gaia BH1, the visible star makes a slow, repeating wobble. That wobble is the clue. The European Gaia spacecraft was designed to measure star positions with extreme precision. It launched in 2013 and observes more than 1 billion stars in the Milky Way. Gaia looks for tiny changes in position. This method is called astrometry. Astrometry means measuring where stars are and how their positions change over time. To human eyes, a star looks fixed. To Gaia, a star can reveal motion so tiny that it would be invisible from the ground. In Gaia BH1, the companion star does not move through space in a simple straight path. It bends, it loops, it follows the pull of something massive and dark. Astronomers also use spectroscopy to study that motion. Spectroscopy means spreading starlight into its colors, like a prism making a rainbow. When a star moves toward us or away from us, its light shifts slightly. This is called the Doppler effect. The same basic effect makes a siren sound higher as it approaches and lower as it passes. With light, motion changes the color pattern by a tiny amount. That tiny shift reveals how the star is moving along our line of sight. So Gaia BH1 was found through motion, a visible star orbiting something unseen, a star moving as though a heavy object is there, a dark partner with enough mass to be a black hole. For a ship arriving after 15,600 years, this matters enormously. The black hole itself would be a poor navigation target from far away. It would offer no bright surface to aim at. It would be a hidden gravitational point. The companion star would become the landmark. That star would be the lighthouse. The ship would track its brightness, its position, its orbit, and its motion against the background stars. From there, the crew could calculate where the black hole must be. They would watch the star swing around empty space. They would measure the timing of its orbit. They would compare its path with centuries of stored predictions. They would look for the place where gravity is acting, even where light is missing. That is what makes this arrival so strange. After crossing 1,560 light years, the ship would not simply point toward a visible object. It would enter a system where the most important thing is discovered indirectly. A normal-looking star would reveal a hidden mass beside it. And the closer the ship came, the more that invisible mass would begin to matter. The first thing the crew would look for is the star, not the black hole. The star. Gaia BH1 has a visible companion, a sun-like star moving around the hidden object every 185.6 days. That is a little more than 6 months. Earth takes 365 days to orbit the Sun. Mercury takes 88 days. The companion star in Gaia BH1 moves on a path between those two familiar rhythms, circling its dark partner in less than half an Earth year. From far away, the system might look almost ordinary. A single point of starlight, a yellowish star, similar enough to the Sun that it would feel strangely familiar after thousands of years in deep space. But careful measurements would reveal the truth. The star would not sit still. It would swing around a hidden center. It would move as if something massive were holding it in orbit. That hidden object would be the black hole. The crew would approach the visible star first because it gives light, position, and motion. It is the practical landmark. The black hole is the destination, but the star is the marker, that tells the ship where the destination lives. To map the system, the crew would use orbital dynamics. Orbital dynamics simply means the rules of how objects move under gravity. The same rules explain why the Moon circles Earth, why Earth circles the Sun, and why Jupiter's moons repeat their paths night after night. When one object orbits another, its speed and path reveal the mass pulling on it. A fast orbit usually means strong gravity. A wide orbit means the object is moving around a larger shared system. A repeating wobble means something unseen may be tugging from nearby. The crew would measure the companion star's position against the background stars. They would measure its speed as it moved toward and away from the ship. They would watch its light shift slightly through the Doppler effect. When the star moved toward them, its light would shift a little bluer. When it moved away, the light would shift a little redder. Those tiny changes would become a map. Each orbit would sharpen the black hole's location. Each measurement would reduce uncertainty. The star would become like a clock hand circling an invisible center. One orbit, then another, then another. And from that motion, the crew could calculate the dark mass beside it. This is one of the strangest parts of arriving at Gaia BH1. The black hole does not need to announce itself with fire. It does not need to be surrounded by a bright disk. It can remain quiet, dark, compact, almost invisible. And still, gravity gives it away. A normal-looking star moves through space in a pattern that only makes sense if something heavy is nearby. Something about 10 times the mass of the Sun, compressed into a region far smaller than any star. The crew might see the companion star first as a warm point ahead. Then, with telescopes and long observations, they would see the deeper structure. A star circling emptiness. A bright object tracing the outline of a dark one. The approach would have to be slow, careful, and mathematical. The ship could not simply fly toward the star and hope to find the black hole nearby. It would need to build a precise three-dimensional map of the system. The companion star's orbit. The black hole's position. The safest approach paths. The regions where gravity becomes stronger. The places where a stable orbit might be possible. The places where a mistake could send the ship into a path it cannot easily escape. The visible star would be the first landmark after 15,600 years. But once the hidden mass was mapped, the mission would change again. The ship would no longer be crossing empty distance. It would be moving inside the gravity field of one of the most compact objects in nature. From far away, the black hole would behave almost normally. Its gravity would follow the same rules as any other object with the same mass. If the Sun could somehow be replaced by a black hole with exactly one solar mass, Earth would keep orbiting at about the same distance. The sky would become dark. The warmth would vanish. But Earth would continue moving around the same amount of mass. Gravity cares about mass and distance. From far away, a black hole with 10 solar masses pulls like any other object with 10 solar masses. A cluster of stars with 10 solar masses. A dark, compact object with 10 solar masses. A strange, invisible point with 10 solar masses. At a large enough distance, the pull can look the same. That is why the companion star can orbit Gaia BH1 without being instantly destroyed. The star circles the hidden object every 185.6 days. Its path reveals the black hole's mass, but it also shows that gravity can be stable from far enough away. The danger grows because the mass is packed into an incredibly small region. A normal star spreads its mass across a huge glowing sphere. The Sun is about 864,000 miles wide. A 10 solar mass black hole could have an event horizon only a few dozen miles across. The event horizon is the boundary around a black hole where escape becomes impossible. For a black hole with about 10 times the Sun's mass, that boundary might have a radius of roughly 18 miles. That means the mass of 10 suns is concentrated into a region smaller than many large cities. This compactness changes everything. Far out, the ship could orbit carefully. Its telescopes could track the companion star. Its instruments could measure gravity, radiation, dust, and light. The crew could build a safe map of the system. But closer in, the curves become sharper. Orbital speed rises. Light bends more strongly. Navigation becomes less forgiving. Near Earth, orbital speed is already fast. The International Space Station moves around Earth at about 17,500 miles per hour. That speed is needed because the station is always falling around the planet. It falls forward so quickly that it keeps missing the ground. Around a compact black hole, the required speeds close in become far more extreme. A ship, trying to hold a tight orbit, would need to move with incredible precision. Too slow, and its path drops inward. Too fast, and it swings away or escapes. At a safe distance, engines can correct small errors. Closer in, those errors grow more serious. Gravity also bends light. This is called gravitational lensing. Lensing means light is curved as it passes near a massive object. The effect was confirmed during a solar eclipse in 1919, when astronomers measured starlight bending around the Sun. A black hole makes the effect much stronger because its mass is so tightly compressed. Near Gaia BH1's black hole, background stars could appear warped. Some could stretch into arcs. Some could appear in more than one place. The dark object would reveal itself by twisting the view behind it. The ship's cameras might see a strange ring of distorted starlight around a black center. That would be beautiful. It would also be a warning. The closer the ship gets, the more space itself is being curved around it. Escape planning becomes part of every movement. A spacecraft near a planet can usually burn its engines and change orbit. Near a compact black hole, a bad path can become expensive to correct. Fuel matters. Timing matters. Angle matters. The ship would have to know where it is, how fast it is moving, and how close it can safely pass. The black hole would not need to pull like a giant monster from across the system. Its real danger begins near the compact center, the place where 10 suns of mass are folded into darkness. The ship could study Gaia BH1 from a careful distance, but every closer orbit would move it toward a region where gravity stops being only a force to measure. It becomes a boundary condition for survival. The famous edge of a black hole is called the event horizon. It is the point where escape stops being possible. Escape velocity is the speed something needs to climb away from gravity. On Earth, escape velocity is about 25,000 miles per hour. That is the speed a spacecraft needs to leave Earth completely instead of falling back. Around the Moon, escape velocity is much lower. Around Jupiter, it is much higher. The stronger the gravity and the closer you are to the object, the faster you must travel to get away. At the event horizon, the required escape speed becomes greater than the speed of light, and light is the fastest speed allowed by the laws of physics. Light moves at about 186,000 miles per second. Nothing with mass can outrun it, so once the escape velocity rises beyond that limit, every route outward closes. That is what makes the event horizon so absolute. It is a boundary around the black hole where all future paths lead deeper in. A rocket could fire its engines. A computer could calculate a perfect course. A crew could try every emergency burn in the ship's memory. Beyond that boundary, all of those efforts still point inward. The event horizon is also surprisingly small for a stellar mass black hole. A stellar mass black hole forms from the collapsed core of a massive star. When a very massive star reaches the end of its life, it can explode as a supernova. The outer layers are blasted into space. The core collapses under its own gravity. If the remaining core is heavy enough, it keeps collapsing until a black hole forms. Gaia BH1's black hole is estimated at around 10 times the mass of the Sun. That sounds enormous. 10 suns of mass. 10 stars worth of gravitational weight. But the event horizon around that mass may have a radius of only about 18 miles. That means the full width across the event horizon could be only about 37 miles. Smaller than many cities. Smaller than the distance across some large metropolitan areas. The Sun itself is about 864,000 miles wide. Jupiter is about 86,000 miles wide. Earth is about 7,900 miles wide. A 10 solar mass black hole's event horizon is tiny compared with planets and stars. That compactness is the source of the terror. The mass is huge. The boundary is small. The gravity changes violently over short distances near the center. Far from the black hole, the ship can treat it like a massive object in space. Closer in, the event horizon becomes the final line. There would be warning zones before that line. The crew would track orbital speed. They would track fuel reserves. They would track gravitational lensing as background stars bent into arcs and rings. They would track radiation from any gas or dust falling inward. They would map paths that remain safely outside the danger region. The event horizon itself would give off no ordinary surface light. The crew would see its presence through what happens around it. Stars distorted behind it. The companion star moving under its pull. Space warped into a dark center surrounded by bent light. If the black hole were feeding on gas, there might be a hot accretion disk around it. Gas in that disk could heat to millions of degrees as it spirals inward. It could release X-rays and other radiation. But Gaia BH1 appears quiet, compared with black holes that are actively feeding. That quietness would make the boundary feel even stranger. A dark object, a small hidden edge. 10 suns of mass compressed into a region only dozens of miles across. For the ship, the rule would be simple. The event horizon is the absolute limit. Crossing it turns the journey into a one-way path. Staying outside it preserves choice. The mission can still observe, still orbit, still measure, still leave. So the real art of visiting Gaia BH1 would be restraint. Getting close enough to study the black hole, far enough to escape it, and precise enough to survive the gravity of a place where space itself has become steep. A safe visit to Gaia BH1 would probably look quiet. No dramatic dive into the black hole. No heroic plunge toward the event horizon. No ship hovering at the edge of no return. The safest mission would study the system from far outside the danger zone. The ship would choose a stable orbit. Stable means the path can repeat again and again without constant emergency corrections. The crew would keep enough distance to preserve options. Enough fuel to leave. Enough time to react. Enough shielding between the living decks and any radiation from the system. From that distance, the black hole would still be scientifically extraordinary. The first target would be the companion star. Its orbit is the map. Every 185.6 days, the star completes another path around the hidden mass. The ship could measure that orbit far more precisely than telescopes near Earth. It could watch the star shift position against the background of distant stars. It could measure tiny changes in the star's light as it moved toward and away from the ship. Those shifts would reveal speed. The path would reveal mass. The timing would reveal the shape of the orbit. Together, those measurements would refine the black hole's weight, location, and motion. A crew near Gaia BH1 could also study gravitational lensing up close. Gravitational lensing happens when gravity bends light. Near a black hole, light from background stars can curve around the dark object before reaching the camera. The result can be strange and beautiful. Stars may appear stretched. Some may appear doubled. Some light may bend into partial arcs. A perfectly aligned source could form a thin ring around the black hole's shadow. From Earth, these effects are tiny and difficult to separate from distance, dust, and telescope limits. From inside the system, the ship could build a detailed map of how the black hole bends the sky. That map would be a direct test of gravity in one of its strongest natural laboratories. The instruments would search for gas too. A quiet, black hole may still have small amounts of material nearby. Hydrogen gas, dust grains, charged particles, debris from the companion star's stellar wind. A stellar wind is a stream of particles flowing away from a star. Our sun has one. It sends the solar wind through the solar system. The companion star in Gaia BH1 may also shed particles into space. Some of that material could drift near the black hole. If gas falls inward, it may heat up and produce radiation. The ship's sensors could look for X-rays, ultraviolet light, radio waves, and faint changes in temperature. X-rays are high-energy light, the same kind used in medicine. But in space they often come from very hot gas near extreme objects. The mission would also measure radiation levels. A black hole itself does not shine like a star, but the environment around it can be dangerous if material is falling in. Charged particles could damage electronics. High-energy radiation could harm tissue. Dust impacts could threaten radiators and exposed instruments. so the crew would likely keep the living sections shielded behind water, metal, and hydrogen-rich materials. The ship might send robotic probes closer in. Small instrument packages could take risks the main habitat should never take. One probe might pass closer to the black hole to measure magnetic fields. Another might study lensing from a carefully chosen angle. Another might sample dust and gas near the companion star. If a probe is lost, the civilization survives. The main ship would remain farther out, watching, measuring, and preserving the ability to leave. That is what a real crewed visit would prioritize. Stable orbit, redundant engines, clear escape paths, radiation shelters, fuel reserves, long-range navigation, careful patience. After 15,600 years, the mission would not need drama to be meaningful. The drama would already be built into the fact of arrival. A civilization born between stars would finally look directly at the object its ancestors chose before any living person existed. A hidden mass, a moving companion star, bent light, quiet gravity, a dark center only dozens of miles across, holding the mass of 10 suns. And for the first time, humans would study a stellar black hole from inside its own system. So if we left Earth in 2026, how long would it take to reach the nearest known black hole? The answer depends on what kind of traveler we imagine. A beam of light would need about 1,560 years. Light leaving Gaia BH1 today will reach Earth around the year 3586. So even our telescopes see that system as it was more than 15 centuries ago. For humans, the numbers become much heavier. Apollo 10 gives us the fastest speed any crew has ever reached. In May of 1969, Thomas Stafford, John Young, and Eugene Cernan returned from the Moon at about 24,791 miles per hour. At that speed, Gaia BH1 would be roughly 42 million years away, about 140 times longer than Homo sapiens have existed. The International Space Station gives us the speed of a place where humans actually live in space. It circles Earth at about 17,500 miles per hour. At that speed, the journey would take about 60 million years, longer than the time since the asteroid impact that helped end the age of the non-avian dinosaurs. Voyager gives us the emotional benchmark, a machine launched in 1977, a spacecraft that crossed into interstellar space in 2012, a probe carrying sounds, images, music, greetings, and traces of Earth. At about 38,000 miles per hour, Gaia BH1 would still be about 27 million years away. Parker Solar Probe gives us the Extreme Machine benchmark, launched in 2018, protected by a carbon heat shield, falling close to the Sun, reaching about 430,000 miles per hour. At Parker speed, Gaia BH1 would still take about 2.4 million years to reach. So current technology fails from every direction. Human speed fails. Living orbital speed fails. Deep space probe speed fails. Even the fastest machine ever built fails. At 1% of light speed, Gaia BH1 is still about 156,000 years away. Longer than cities, longer than writing, longer than settled farming. At 10% of light speed, the trip becomes about 15,600 years. Finally, short enough to describe as a mission, but still far too long for one crew. So the ship changes. It stops being a spacecraft in the ordinary sense. It becomes a moving world. It needs air, water, food, farms, waste recycling, medical care, schools, laws, archives, gravity, shielding, power, and repairs. The first crew would never arrive. Their children would never arrive. Their distant descendants would inherit the mission. Earth would become a delayed voice. Near Gaia BH1, a message from home would take 1,560 years to arrive. A reply would take the same amount of time to return. A single exchange would stretch across more than 3,000 years. By then, the mission might be history, or myth, or ceremony, or a promise preserved by people born between stars. And after all of that, the destination itself would be hidden. Gaia BH1 is found through the motion of its companion star, a sun-like star orbiting every 185.6 days around something dark. The black hole is estimated at around 10 solar masses, 10 suns of mass compressed into a region whose event horizon may be only a few dozen miles across. From far away, its gravity behaves like the gravity of any object with the same mass. Closer in, the compactness changes everything. Light bends, orbital speeds rise, escape paths become unforgiving. The event horizon becomes the absolute limit, a boundary where escape velocity exceeds the speed of light. Crossing it means every future path leads inward. A safe mission would stay far outside that boundary. It would study the companion star, measure warped starlight, map gravitational lensing, search for gas, dust, radiation, and signs of material falling inward. Robotic probes could move closer while the main ship stayed protected, cautious, and ready to leave. That is the final shape of the journey. The nearest known black hole is close in the language of the Milky Way. And still, reaching it would demand speeds, lifetimes, societies, and patience far beyond anything humanity has ever attempted. Black holes are terrifying because they are places where gravity wins completely. But the nearest one teaches something quieter too. The galaxy is so large that even its nearby darkness is almost unreachable. The nearest black hole is close enough to be our neighbor, and far enough to show how small, slow, and temporary we are against the scale of the stars.